In this video, I want us to take a look at some what we call decay processes. And when we talk about decay, things are breaking down, and these are nuclear processes. So the focus is with the nuclear parts of whatever atom what we're looking at. So we're going to be looking at examples of one atom at a time, but keep in mind this is happening with an incredibly huge number of atoms pretty much simultaneously. And that's where all the energy comes from. It's the fact that you have so many atoms at one time undergoing these processes. So we're going to look at three different processes. We're going to look at alpha decay, beta decay, and gamma decay. All right, jump in and take a look. All right. Uranium-238 is undergoing alpha decay. What are the products of the reaction? So in a nuclear reaction, what we need to keep in mind is that it's just the parts of the nucleus that we are focused on. So we're only focused on protons and neutrons. Typically, we're not going to be worrying about electrons. There will be a special case, an example that we're going to have here shortly. But right now, for the most part, when you're talking about a nuclear reaction, you're talking about changes with the nucleus. No matter what, there's changes with the nucleus. So this is an example of a decay reaction, so like a nuclear fission reaction. So let's jump in. Uranium-238. So I like blue. So let's go with our, oh sorry, need the tool. So let's go with our uranium. We got 238. The number lets us know the mass of the isotope. And so now we need a periodic table. Unless you've got this memorized, probably don't. So let's zoom in to uranium. It's down here where the actinide series is at, and we see there's uranium-238 and it has 92 protons. So let's go back so we know that the atomic number is 92. Okay, so I'm going to draw a yield arrow, and I'm going to draw the alpha symbol above it. It's just a way to denote, a way of us showing exactly which process is occurring, if it's alpha decay or one of the other fission processes. So now what you need to remember is this: an alpha particle is always, and actually I'm going to point down elsewhere, it's always going to be a helium-4 atom. Okay, so an alpha particle is always a helium-4 atom. So we go back to our periodic table. Let me come over here to where helium is. Then we see that it's the mass of 4, so we would say helium-4, and helium has 2 protons. Okay, so we're going to go back, and we know that our atomic number is 2. Now at this point, it literally just becomes a grade school math problem where all the numbers across the top and all the numbers across the bottom have to equal each other out. So remember that the arrow, the yield sign, all right, it just means to make or to produce. To yield means to make or to produce. So the question right now is what product do we put here? So far, what are the products of this reaction? We have a helium-4 atom, which is, we're going to, from here on out, we will refer to this as an alpha particle. Okay, and actually, I'm going to back that up just a little bit. An alpha particle. All right, so alpha particle, always a helium-4 atom. So the question, what's left over? Well, we can get rid of the question mark, and let's just do some math. If we have 92 protons in this nucleus right here, and it breaks apart, and what is emitted is something that has a mass of 4 with 2 protons, then that means that there still has to be 90 protons still left in that original particle. If a total mass number of 4 is lost from 238, then we can see that we have 234. So you can see across the top, 234 plus 4 equals 238, and 90 plus 2 equals 92. So no matter which way you go with the math, it balances itself out. Now we just ask ourselves, which number do we need to identify the isotope? And is it the 234 or is it the 90? And we know it's the 90 because the bottom number on isotope notation identifies the atomic number. So in the atomic number, the number of protons defines the atom. So we go back down here to our actinide series, and we went from 90 and we lost 2 down to 90, or we went from 92 down to 90. So what's left over is, with 90 protons, would be a thorium atom. Now right here you see it says 232. That is the average mass for thorium isotopes right there, based on the abundance of isotopes. Remember, the numbers on the periodic table represent the most common abundant form, stable form. So we're down to atomic number 90, so that's thorium. And the isotope that we have is thorium-234, not the 232 that you saw on the periodic table. That 232, remember we said that is just the average atomic mass based on the abundance of all the different isotopes that are out there. Okay, I'm just going to erase that, get that out of there so that next time we come here, we have ourselves a nice clean slate. All right, so that equals that's it. So now what we do is we call this new product here, we call it a daughter product. All right, this is a daughter product. So the reason for that, if you think back to biology with like mitosis, when you had a cell and it broke apart into two cells, you divided it into two new cells, kind of a division process. Those were called daughter cells. So the new things that come from the old. So those were called parent cells. We don't call the uranium-238 here a parent nucleus. I mean, I guess we could, but it's typically not referred to that. It's the particle that is undergoing this nuclear reaction. All right, so let's slide on down. Let's take a look at something else. Let's look at a beta decay. All right, so beta decay. We got carbon-14, so I'm going to put carbon-14 undergoes beta decay, so I'm going to draw an arrow, and I'm going to draw the Greek beta symbol. All right, carbon-14, we zoom in, and carbon is carbon no matter what. This is carbon-12 on the periodic table, but we need carbon-14, which still has 6 protons. So we're going to go back, put our 6. All right. So it says it undergoes beta decay. So beta decay, what you need to know is in beta decay, neutrons that are in the original atom, they break apart into a proton, and then when that happens, an electron is emitted out. So let me do this. Let's just say that, so we've got 1, 2, 3, 4, 5, there's 6. We're going to say those 6 represent our protons that we have right here in the carbon-14. And then let's go with, I'm going to go with red for some good contrast. So if there's a mass of 14 and 6 protons, then that must mean that there's 14 minus 6, there are 8 neutrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7. Let's just put it there. All right. So now we use a different color here. If one of those neutrons, and we said the red here are the neutrons, if a neutron breaks apart and emits an electron out of the nucleus, then that is a product that is produced. So we can come over here and put electron, and we know we have 1 electron, and we ignore the mass of electrons when we're talking about the mass of a nucleus. So what we can do is we can come here and put a 0, all right? And so that's a 0 on the top because there's no mass, and we see we have 1 of those particles. All right, so now the question is what is left? Well, we know that there's going to be energy. That's not a problem. All right, we've got that. So let's go back to what we originally had. We see here we had 1, 2, 3, 4, 5, 6 protons. All right, so 1, 2, 3, 4, 5, 6 protons. And then we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. But one of those neutrons, the one that we are showing the electron emitting from, has broken apart and become a proton. So now, let me draw this out for you. So 1, 2, 3, 4, 5, 6, 7, 8. So we've got 1, 2, 3, 4, 5, 6, 7, 8. But one of those, we'll just go with the last one, breaks apart into and becomes a proton. So now you can see we have 1, 2, 3, 4, 5, 6, 7 protons. And we have 1, 2, 3, 4, 5, 6, 7 neutrons. 7 plus 7 is still a mass of 14, which works. This makes sense because 14, if you look across the top of our isotope notation here, 14 plus 0 equals 14. And going across the bottom, 7 plus a negative 1 gives us 6. We're done. And so now you need to know that an electron emitted from the nucleus of a radioactive isotope, that is what we call a beta particle. And so what we have to do is ask ourselves right here, what is our daughter product, right? Well, for that, go back to the periodic table, and we see that atomic number 7 is nitrogen, and it just so happens to have a mass of 14. It balances out because remember we lost no mass from this beta breakdown, right? So I'm going to come back here, and I know that we have nitrogen right here, and so there's our nuclear reaction for the beta decay of carbon-14. Let's do one other example. I want to look at gamma decay. We have radium-226. Okay, so let's go to the periodic table. Let me pinch the zoom back. And radium is down here at the very bottom of period 2. So radium-226, and it has a mass of 88. I'm sorry, it has an atomic number of 88. The mass is 226. So this is undergoing gamma decay. So in gamma decay, what happens is the element itself, the atoms themselves. We're looking at one atom, but there's usually a bunch of atoms here. They are already energized, and so we show that by putting an asterisk on it to show that it's radium-226, but we would say it has some ionizing energy that can be released. All right, and so the way we do that is you kind of draw a little squiggly line, and squiggly lines tend to represent like energy flow, like photons or light energy and stuff like that. So we get this energy release, and what we're going to do is say we're going to put this little gamma symbol right there. Okay, and so when that energy is released, it hasn't broken apart into some other element. It's still the same element. It's just less energized. Okay, so now what we do is we write radium 226, 88, and then of course there was the gamma energy that was released. Okay, so remember this little squiggly. Ooh, that's not that squiggly, is it? So this little squiggly, we're going to go with that. We're going to say this represents like ionizing energy. Okay, that's what that represents. And there you have a gamma decay problem. Gamma decay is pretty straightforward. You just have to have that asterisk there at first to show that it's energized. You show the energy coming off of that, and you're done. That is it. 3 easy examples, but I think they're examples that you can wrap your mind around. All right. So study, and I'll see you at another video real soon. Take care. Stay curious. Bye. And that's it. Alpha decay, you will always have a helium-4 atom that's being emitted from the nucleus, and so we draw that as a product off to the side as you saw. Beta decay, there's an electron that's emitted from the nucleus, while one of the neutrons is there, ends up shifting its properties, its characteristics, to be like a proton, which then increases the atomic number, and as you saw, that's how you get a different element from that fashion. Instead of parts that are from the nucleus breaking off, you get them switching properties, which effectively change the atomic number. And then gamma decay, you've got these atoms that are just highly energized, and they just are able to release that energy under those particular conditions. And when that happens, it's still the same element. It isn't changing its form, it's just releasing that energy, and usually these are in huge bursts. Again, these are nuclear reactions. So when we're talking, and you've heard of, hopefully you've probably heard of some gamma energy. So it is a huge amount of energy, very, 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 very powerful. So with that said, I don't know, it was pretty straightforward, pretty easy. Be doing some more practice problems on these later. I just thought it was a good idea to give a quick summary for each of the 3 basic fission reactions, and then we'll kind of go from there. Be on the lookout for some more problems here real soon. It's good talking with you. Stay curious, and I will see you soon for another video. Bye.